Yeah, I'm starting the session. I'll share my screen. Yeah, see here. So today I will show you how to use this EDA playground. Okay, EDA playground. My screen is visible, I think so. Okay. So I will use this EDA playground. So this is my EDA playground. This is open source EDA playground. Here what I can do, just you can register with your mail ID, Gmail. You can register with your Gmail. So already registered and I'm logged in. So in by using this VDA playground, you can write the Verilog codes as well as system Verilog codes. Okay. So here I can write the design and here I can write the test bench. Okay. So here suppose if I am writing simple program, like we already discussed about the data types, no, we already discussed about the data type. Okay, suppose I'm using here I am writing the design. Okay, here I am writing the code design. Okay, like module let us take test module test, mm, reg a reg a and b reg b. I'm using initial. Okay, initial and next begin, initial begin. Okay, initial begin and next what I am doing, b equal to a, b equal to a. I'm displaying just a dollar display the value of a. Okay, so here I am writing the design. The value of a is, okay, so there is a format specifier means so here you are using if you want to display binary, you can use a format specifier, that is percentage b. Okay, if you are using if you want to display integer, you can use a format specifier percentage d. Okay, if you want to display octal, you can use percentage o. If you want to display hexadecimal number, you can use percentage h. Okay, here I want to display decimal. Okay, percentage d comma b comma b. Okay, so semicolon. Next I need to end the module. Okay, I wrote if multiple lines of codes are there, you need to write between the initial, begin and block end module. Okay, so this I wrote the program simple related to the basic reg data type. Okay, so what is the default value of register reg data type? What is the default value of reg data type? As I told you in the last class, the default value for wire data type is z, and the default value for reg data type is x. Okay, here it will display what value x. Okay, b I am initializing to what a. Okay, b I am initializing to a. Okay, this is a simple value, so it will display the value of a is what x, it should display. Okay, so when you are writing the program, so here go to tools, select Aldec Rivera. Okay, this is Aldec Rivera. This is one type of FPGA. And languages, I told you know, it will support system Verilog and Verilog. Okay, languages, you can try the programs in for system Verilog as well as Verilog. Okay, so here what you are doing, just save this file. Okay, save this file, save this file and run this file, run this file. See here, I got, so in the log file I got the value of a is what x, the value of a is x. Okay, so like this I can use this EDA playground, and this one I can write in Xilinx Vivado also. Okay, Xilinx Vivado if you take, so just I am opening the Xilinx Vivado. This is Xilinx Vivado. So Xilinx Vivado is big software. It will take about around 35 GB of size in your C drive. Okay, it's a big software. So here we can use Xilinx Vivado, Model Sim and Questa Sim for writing the programs. By using Model Sim and Questa Sim only we can simulate that. Okay, quarters prime also we can use quarters prime. By using this quarters prime and Xilinx Vivado, we can elaborate the design, and we can see the circuit. Okay, we can see the circuit. Okay, so just a simple program I'm writing. If you want to create a project, go to project, create the project. Okay, create the project. Next, here I'm giving a project like data types. I'm giving the project name as what, data types. Okay, data types. You need to select the path wherever you are storing the that value, that programs. You need to select the path. That path you need to remember. Okay, that path you need to remember. Okay, so here just here in this I am writing the programs, Verilog programs. Now next go to next. Next, you need to create the file. So what file I'm using, I can use to test reg data type. Okay, reg underscore data type I can use, data type reg underscore data type. Okay, okay, I'll keep okay. Next, next. So I need to so automatically default FPGA board it will select. Okay, so this is the part number of FPGA board. I will keep next, and I will keep it next. So project will be created. Project will be created. So the project is created. So it is asking module name is same name, means okay, I am giving same module name. Okay, I am giving same module name. So this one I am closing. Here there are two sources are there. So whatever the design is there, you need to write in design sources. Whatever the test benches are there, you need to write in simulation sources. Suppose one more design source if I want to add, go to design source, add this design source, and you can give the create file, and you can give the design source. Okay, so like suppose same program I'm using wire data type. Okay, suppose if I'm using wire data type, I'll create a one more design source, create I'll use a wire underscore data type, wire underscore data type. Okay, so this also I will create. Okay, finish. So this will be added into this this design source. Okay, so you need to give the name such a way that that should be remembered. Okay, reach underscore data type. Okay, so if you double click this, I will get this. Okay, so this one you can delete. Okay, so this one is not required. And next, what I need to do here, I wrote the program, no, where I wrote the program, EDA playground. Okay, this one just I am copying, and I'm pasting here. Okay, I'm pasting here. So after pasting, you need to save that file. Okay, you need to save that file, and in order to simulate that file, go to simulation, run behavioral simulation, run the behavioral simulation. Run the behavioral simulation. So it will execute due to earlier error. Some errors are getting. Okay. 1 second. Initial begin means reg. Okay. Should display initial begin. Yeah, I got this. See here. So I got so you can see the output in TCL console. You can see the output in TCL console. What is this? The value of A is what? X. The value of A is X. Okay. So like this, we can use this reg data type. Okay. So the default value of A is what? X. Okay. So like this we can see. Okay. And other program I'm writing. Suppose like I'm using I'm using vectors and arrays concept. Okay, so like module test 2. Okay, reg what I am giving 2 is to 0, 2 down to 0, 2 down to 0. This is nothing but vector, and mem of how much size I am giving, 3 down to 0, 3 down to 0, mem of 3 down to 0, initial, begin, okay, mem of 0, okay, mem of 0 equal to what? Mem of 0 equal to 3 tick binary 0 double 1, okay. Mem of 1 equal to mem of 1 equal to mem of 1 equal to what? Mem of 1 equal to 3 tick binary 1 1 1 1, okay. And and next mem of 2 mem of 2 mem of 2 equal to 3 tick 1 second, 3 tick binary 101, okay, 101, okay. So if I want to display, so just a display this is the system task, the value of mem is let us take percentage b, okay, percentage b, okay, percentage b comma so mem of percentage b, mem of 0 is percentage mem of 0 is percentage b, okay, mem of 0 is percentage b, and same, okay. So mem of 1 is percentage b, mem of 0, mem of 1, and mem of 2, okay, is percentage b, is percentage b, 1 second, mem of 1, and here mem of 0 comma mem of 1 comma mem of 2, okay. Here I am giving like this, okay. End module, okay. So just I am running this program. Some error I am getting, okay. So if I remove this if I run this end module, okay. Syntax error initial begin, okay. This I will see. So like this we can like program in the Xylix Vivado and this EDA playground, okay. So like this I can run some programs also in Xylix Vivado, okay. Suppose like design and the next Verilog programs, okay. Verilog programs suppose data types are there. 1 second, data types, so this is one more data types. If I open this, I wrote the programs related to data types, okay. Xylix Vivado, by using Xylix Vivado you can write the programs, okay. Yeah. it's not there. Okay, one second. Okay, test I wrote. I will see this test. Wide data type. Okay, wide data type if you see. So what is this wide data type? Not intro. Test see here. Same program I wrote. Okay, whatever I explained, that same program I wrote. Okay, so this is about total EDA playground and Xilinx Vivado. Okay, so next we'll go with next topic. One second. Next topic. Today's topic is port rule connections. Okay, today's topic is port rule connection. That we'll see. Okay. Verilog port rule connections. Port rule connections. Okay. So what are these Verilog port rule connections? We'll see. Okay. So suppose if you are writing for so basically port rule connections will be suppose one second. Yeah, I think my screen is visible, no? Okay, just to give response. Okay, yes, it's visible. So port rule connections, the port rule connections, that will be like this. Suppose you have suppose if you are writing for any full adder circuit. Okay, so this will be like this. Suppose port rule connection, so you need to remember this port rule connections. Suppose if you are writing any DUT or test bench, here so here your driver, this is nothing but driver. Okay, so this is nothing but driver. Inside there is a design. Inside there is a design. Outside, what is outside? Outside is nothing but design under test. DUT. Okay, so that means input for this design can be what reg data type or net data type. Okay, reg data type or net data type, and input for this design should be net data type. Should be net data type. This input is net data type. Okay, and output from the design. Output from the design. This is output of the design. Okay, output of the design can be what it can be reg or net data type. Okay, and output of this whatever the DUT is there, it should be net data type. It should be net data type. And for this one there is inouts are there, some signals are there, those are acting as inouts. Inouts means what? Input and output. Okay, so these are nothing but we can call as a net these are net data types. Okay, so these port rule connections you need to follow. Okay, so port rule connections you need to follow. Suppose if you are writing for program for what full adder circuit. Okay, so full adder means so here you know the full adder circuit. So full adder have how many inputs? You already seen in the digital, no? Full adder have how many inputs? 3 inputs. Those are A, B and C. Okay, and 2 outputs, those are nothing but sum and carry. Sum and carry. This is full adder circuit. Okay, full adder circuit. So full adder. So here for this, so this is my design. Okay, suppose this is my design. This is my design. Okay, this is full adder circuit. So here inside these are the inputs for the design. Okay, these are the inputs for the design. Okay, inputs for the design. To check whether this functionality is correct or not, you need to write the test bench. You need to write the test bench. Okay, so this is nothing but what TB. You need to write the test bench. Okay, so TB also you need to give the inputs. Okay, just 1 minute. I'll come. 1 minute. Yeah, 1 second. Yes. Okay. So here you see. So where we are. Okay. So this is a full adder. So this is test bench. So test bench also you need to give the inputs. Okay. So test bench also you need to give the inputs. These are nothing but what test bench inputs. Okay. You are giving the test cases, and design will give the output. Design will give the output. From this you will getting the output for the test bench. This is sum and carry. Sum and carry. So here you need to remember that these test bench inputs can be what reg or net data type. Reg or net data type, and these inputs should be which data type means net data type. That is y data type. Okay. These outputs can be what these outputs can be outputs of the design can be reg or net or reg data type, and these outputs of the test this test bench should be net data type. Net data type. Okay, these port rule connections you need to follow. Okay, port rule connections you need to follow. Suppose for the input if you are using reg data type, reg a input reg b. Okay, reg b. So compile will throw an error. Okay, input cannot be what input cannot be reg data type. Okay, output can be reg data type. Okay, so so these are the you need to remember. Suppose if you are writing program for simple AND gate. Okay, simple AND gate you are writing. So simple AND gate means what? Inside there will be a design. Simple AND gate. Simple AND gate means what? What are the inputs and outputs? A, B are the inputs, and let us take output is Y. Okay. So here you are writing the program. Just this one is nothing but AND gate design. Okay, AND gate design, and this is test bench. This is nothing but what? Test bench. Okay, so test bench. So for this these are the design inputs and these are the design outputs. Okay, and for this design inputs I am giving the test bench inputs. Let us take the test bench inputs are a underscore tb and b underscore tb. Okay, and outputs are y underscore tb. Okay, so from this design this port rule connections, this should be what for test bench inputs. It can be what reg data type or net data type, and this should be design input should be what net data type only. Design input should be net data type. Okay, and next 1 second, I will keep my charging. Okay, 43 minutes are there. Yeah. Okay. So here this is what this can be output can be net or reg data type, and this output of the test bench should be net data type. Net data type. Okay, suppose I will tell you the modeling styles. In the starting of the class I told you the modeling styles. So when I am writing the program in the behavioral modeling, so how I can write this program? So this program for the AND gate I can write module and module name. I am giving module name as AND underscore gate and underscore gate. I am initializing what are the inputs, input a comma b, and output. So here if you are using the behavioral modeling, output you need to use as reg data type. Okay, output always you need to use reg data type. Okay, always at the rate star. Always at the rate star. Okay, star means what? This is implication operator. Okay, implication operator means if there are some 100 inputs or 50 inputs, if there any change in the input, you will get the change in the output. Okay, so this is nothing but suppose this one I can write like this also. Two inputs are there, no? Always at the rate a comma b I can write. Okay, as this is a combination circuit, if there any change in the inputs, if there any change in the input, there is a change in the output. Okay, so I can write begin I can write begin that y equal to what? Y equal to a and b. Y equal to, I can write a and b, end and end module, end and end module. Okay, so this is design. Okay, this is nothing but design. Okay, so in this port rule connections there are two types are there. One is what for this AND gate I need to instantiate. Okay, I need to instantiate this design. Okay, so how to instantiate this designs, the instantiation of this design. Instantiation is nothing but suppose full adder is there. Full adder, you design the full adder by using two half adders and OR gate, no. So for writing the program for full adder, first you write the program for half adder and instantiate for how many times? Two times. Instantiate for two times. That is nothing but instantiation. Okay, calling the design. That is nothing but instantiation. Okay, so there are two types of instantiations are there. Okay, instantiation. Instantiation of design. Okay, so one is what? One is connection by name. Connection by name, and another is connection by name, and another is connection by position, connection by position with order list, okay, connection by position with order list. Okay, so here so how I can write the connection? First we'll see the connection by name. Okay, so connection by name is, for this I want to write the test bench. Okay, so test bench, so I am writing module TB, okay, I am using this wire a underscore TB, b underscore TB, and c underscore TB. Okay, c underscore TB. Okay, and I think in test bench output should be y data type and input should be red data type. Okay, so here what I can do? So output I am considering as what? Y data type. Outputs I am considering a y data type. Okay, port rule connections, if you see the test bench we already seen, no. So here, see here, output should be net data type. Okay, input can be either reg data type or net data type. Okay, so if you are writing for the test bench, so what I can write? So that means test bench inputs. So here, so wire y underscore TB, reg a underscore TB, and b underscore TB. Okay, next you need to initialize the reg variables. I am using some concatenation operator, a underscore TB and b underscore TB, that is equal to 0. Okay, and next I am instantiating. How I am instantiating? Connection by name. So connection name by name will be, syntax will be like this. What is the syntax? Connection by name. So here design name, and next instance name, design name, instance name, and dot a underscore TB, dot b underscore TB, comma, dot c y underscore TB. Okay, so that means here I can write what I can write? So here you see, so and underscore gate, this is what? This is my design name. Okay, this is my design name. Okay, and after that, and underscore gate, and what is my instance name? Let us take a1. Okay, instance name will be like this. Suppose if you draw the AND gate, this is what? A, B, and this is Y. Let us take this instance name is a1. Okay, that is the instance name, bracket, dot a. Dot a is nothing but what? Design input. Whatever the bracket, in the bracket you will get the test bench input. Okay, similarly dot b underscore TB, comma, dot y underscore TB, like this you will get. Okay, so like this you can instantiate connection by name. Okay, this is nothing but connection by name. Okay, suppose if you want to write for the AND gate by using continuous assignment, so how I can write? So here I'm using by using this is data flow modeling, that I will tell you in detail. Just I'm writing here, I'm using data flow modeling. So data flow modeling, what I can write, module and underscore gate, and underscore gate. What are the inputs? Input a comma b, next output. What is output? Output is y. Okay, I need to use a continuous assignment statement, that is assign y equal to what? A and b. Y equal to a and b. Okay, so this is a bitwise operator. Okay, and next end module. Next I am writing module under top. Okay, so I am initializing where I can use x y z. Okay, so I need to instantiate. How I am instantiating and underscore gate and instance name whatever you can do. Okay, you can take. Okay, that is your option. Okay, and a design input, and this whatever the design and test input, test bench input, and design input and test bench input. Okay, so like this, end module. Okay, so like this you can write in the data flow modeling also. Okay, data flow modeling also you can write. Okay, so like this, suppose if it is connection by order, so connection by order means what? So same program I'm writing with connection by position with order list. Okay, so how you declared this inputs and outputs in the design, the same model you need to follow in the connection by order. Okay, connection by position with order list. Next is what? Second one, connection by position with order list. Okay, connection by position with order list. Okay, so how I can write? Module and underscore gate input a comma b. Okay, next output. What is output? Output is y. Okay, output is y. I need to use a continuous assignment statement, that is assign y equal to what? A and b. Y equal to a and b, and end module. Okay, so I am writing module under top. Okay, I'm using connection by position with order list. No, so where x y z. Okay, I need to instantiate. What is the design name? This name and this name should be same. This one, this is the module name. No, this name should be same. Okay, instance 1 I am giving. I can give the inputs. First I declared the inputs. No, here also I need to declare the inputs, x y and output. What is the output of y? Okay, so x y and z, and end module. Okay, so end module. So like this we can instantiate. Okay, so we can instantiate like this. Okay, suppose like in the digital we already seen the full adder by using half adder. No, how to design this full adder using by using port rule connections, full adder by using half adder. Suppose if it is full adder by using half adder, using half adder. Okay, full adder using half adder. So so how this will look like? Two half adders are there in digital. I think you came across this. We are designing the full adder by using two half adders. This is half adder 1 and half adder 2. Okay, and let us take the design inputs are what? Two inputs are there, a and b. Okay, and two outputs are there, sum and carry. Okay, here also two inputs are there, a and b, and this is sum and carry. Okay, and in between this sum is given to this half adder. Let us consider this one is what, this one is net means what, w1, okay. And design under test, this design under top level design, this is nothing but total my full adder design. This full adder design, full adder have the inputs, no? So that inputs you need to consider as what, that inputs are nothing but a underscore full adder, and next here also b underscore full adder, b underscore full adder, and next you are getting sum, this is sum, and this is given to output, this is nothing but sum underscore full adder, okay. And carry, so let us take this carry, this is the in intermediate variable. Here also you are getting intermediate variable, that is this is let us take w3, okay, w3, and this one is given to OR gate, this one you are given to OR gate, okay. And let us take this is w2, and this is w3, okay, w3. And carry input of full adder is there, no? One more input, carry input, okay, carry input of full adder, it is giving, we are giving to which one, this b input, okay, we are giving to the b input, this b input, okay. So here how I can write, so for the first you need to write the program for half adder, okay. So how I write the program for half adder? Simple, like I am using data flow modeling, module half adder, half underscore adder, okay. What are the inputs? Input a, and I'm initializing input b, okay, comma, and next output sum, and output carry, okay, output carry, and next assign. So for half adder you have sum equal to what, sum equal to a XOR b, no? Carry equal to what, a and b, so assign sum equal to what, a XOR b, okay. And assign carry equal to what, a and b, okay. So end module, I wrote the program for which one, half adder. First I wrote the program for half adder, okay. Next I am writing the program for what, full adder, okay, that is top module, okay. So here if I am writing the program for full adder, so I am using module full adder, okay, full adder. What are the inputs? Input a underscore fa, comma, input b underscore fa, okay. Next input c in underscore fa, okay. Output sum underscore fa, and output carry underscore fa, okay. So here intermediate variables are there, no? Intermediate variables, what are the intermediate variables? W1, W2, W3, okay. So I need to consider as wire data type, okay, that is nothing but wire data type, okay. So wire W1, W2, W3, okay. So here if you see this half adder circuit, W1 equal to what, so that means for this one, what are the outputs? W1 and next W2, okay. These are the inputs, okay, these are the output for this top module. And what are the inputs? A underscore fa and b underscore fa. Okay, and for this half adder, w1 is output, w2 is also one more output. Okay, so I will write connection by name. Okay, connection by name, how I am writing, just observe. So here I am writing the design name, whatever the design name is there, the design name and this name should be same. What is my design name? Half underscore adder, no? So half underscore adder, and let us take the instance name is ha1. Okay, small ha1 will give small ha1, and this is small ha2. Okay, so here how I can write half design name, half underscore adder. What is my instance name? ha1. Connection by name I am giving dot a underscore fa. Okay, dot b. Okay, dot b underscore fa. Okay, and dot s is the design output. Okay, what is the output of this top module? w1. Okay, dot c is the design output. What is the output of top module? w2. Okay, w2. Okay, see here, just observe here. So this is a and b are the design inputs and outputs, and a underscore fa, b underscore fa, and w1 w2, these are the outputs, inputs and outputs of my top module. Okay, so here this is instantiation. I need to instantiate how many times? Two half adders you are using, so two times I need to instantiate. Okay, so next instantiation, half underscore adder ha2 dot a this is what? w1. Okay, w1 comma dot b dot b w1 is input. Okay, w1 is input, and what is the input for this b? C underscore fa, no? Input for this b c underscore fa, and here w1, these are the inputs for this top module. Okay, and what are the outputs? Outputs for the top module is sum underscore fa and w3. Okay, so here if you write a is w1, b c in underscore fa, comma dot s sum underscore fa. Okay, sum underscore fa, comma dot c w3. Okay, w3. So this is nothing but connection by name. Okay, after that what I need to do? I need to use a continuous assignment statement, that is assign. Okay, carry underscore fa. Okay, so carry underscore fa is nothing but you are using which gates? R gate, no? So this is nothing but carry underscore fa. So you are getting w2 and w3. These are the inputs. Okay, w2, w3 and w3. Okay, so I can use a logical operator. What is that? w2 and w3 and end module. End you need to write initial and begin. You need to write here. Here multiple statements are there, means you need to write initial begin. Okay, where here after the declaring these wire variables, I need to use initial begin. Okay, and initial begin, and here you need to write end. Okay, you can't use assign statement between the initial and begin, and so at last what I am writing, I am using a continuous assignment statement, assign carry underscore a full adder equal to w2 or w3 and end module. Okay, so like this I can write the program for this. This is nothing but connection by name. So what I did, so like this you can write the program for parallel ripple carry adder also. So ripple carry adder, how many full adders you are using? 4 full adders you are using. Okay, there you can use connection by name by using this instantiation. Okay, so this is the program. Is it fine? Any doubt in this? Yes, shall I move forward? Okay, so this is the full adder by using half adder. Okay, so just I will see the program whether I wrote or not. I will show you. Okay, just I'll show this program. Once again, Adel design, Verilog programs. So here, adder subtractor, combinational logic, full adder using half adder. Yeah, full adder using half adder. We'll see full adder using half adder. Yeah, yeah. Here you will see. This is full adder. Okay. So first I wrote for half adder. Okay. First I wrote for what, half adder. Okay. I'm closing this. Okay. First I wrote for design for what, half adder. Okay. So what is this? I think it's visible. So just design for half adder. First you need to write the half adder. Okay. So so this is the half adder circuit. So I'm deleting. Yeah, see here. So just I wrote the half adder circuit. So this is the program for half adder. Module half underscore adder. Input a comma b, output sum comma carry. Assign. I'm using assign statement. Sum equal to a x or b, and assign carry equal to a and b, and end module. Okay. So first I wrote for the half adder. After that, what I wrote. So by using this instantiation, I wrote. So I used two half adders. So that is it went into instance name. That means two half adders it game went. Okay, it is added in within the module. Okay, within the module it is added. So this is the program for what, full adder. This is the program for full adder. Okay, so if you see the program for full adder, this is module full adder. Inputs, what are the inputs? A underscore fa, b underscore fa. Outputs are nothing but sum underscore fa, carry underscore fa. Okay, whatever I explained in that code, I am just explaining here. So wire I need to initialize, no, wire w1, w2, w3. Half underscore adder ha1 is instance name. Dot a, f underscore a underscore fa, dot b underscore fa. Sum and w1 dot carry w2, and half adder, that means half adder 2 dot a w1 dot b c input underscore fa dot sum underscore fa dot carry w3. Okay, assign I need to use carry underscore fa equal to w2 or w3. Okay, so this one I can elaborate the design. Okay, so this is nothing but I wrote in the top module. So go to run and run simulation. Not run simulation. If you want to like see the design, go to elaborate design. Okay, save this file. Go to elaborate design. Just if you want to see the hardware circuit, you can go to elaborate design. See here. Can you see this design? So that means this is nothing but I designed the full adder by using two half adders and one OR gate. Okay, so these are nothing but what, my design inputs. A and B, carry and sum are nothing but my design inputs. Okay, and next in between, this is A underscore fa, B underscore fa, carry underscore fa, and sum underscore fa are nothing but the input for the full adder circuit. So okay, so like this you can elaborate the design. Okay, you can elaborate the design. So that design will be, you can see the hardware circuit. Okay, yeah, hope you understood this instantiation. Today we discussed about this instantiation, no? Okay, connection by name and connection by position and port rule connections, and so like that, full subtractor using full subtractor using half subtractor also I did. Okay, so just I'll show you. same thing. What is this full subtractor using half subtractor? Just we'll see. Yeah, full subtractor using half subtractor. First what I did, I wrote the program for half subtractor. Okay, so first I wrote the program for which subtractor? Half subtractor. Okay, so after that what I did, so this I will delete. Okay, not required. So that means half subtractor, half underscore subtractor. Okay, same a and input a, input b, and output difference and borrow. Assign difference equal to what? A XOR b. Assign borrow equal to what? Borrow you'll get a bar b, no? So not of a and b, not of a and b. Okay, so first I wrote, after that what? Full subtractor I wrote. Okay, this is the code for full subtractor. So in this also I can use two full subtractors and one OR gate. Okay, so here if you see, so see here, so that means module full subtractor, inputs I am defining. Okay, input a, b and b in, and output difference and borrow. In between those intermediate variables are there, that I am initializing as wire d1, b1 and d2. So this next I am instantiating first half adder. Okay, dot a by connection by name. Okay, and for second half adder by connection by name. Assign borrow equal to what? B1 and b2. Okay, end module. Okay, so this is a full subtractor by using half subtractor. So if you want to design, see the design, just go to RTL analysis and open the elaborated design. If you open the elaborated design, you can see the circuit. Okay, see here. So two half subtractors are there. So input for the half subtractors are A, B and borrow and difference. A, B and borrow difference. And this borrow is connected with this OR gate. You are getting borrow. And difference is same, no? Some for full adder and full subtractor. Difference and sum is same. That is A XOR B XOR C. A XOR B XOR C. So if you add, so this is so if you press this, so this is the design. This is the one half subtractor. So difference equal to what? A XOR B, and borrow equal to A bar B. Okay, borrow equal to A bar B. Like this you need to do. Okay, you need to do. Okay, so like this. This is the design. Okay, so like this you can elaborate the design and you can analyze the design. Okay, whatever you studied in the digital, just I'm writing in textual format, and I'm simulating this the waveforms and elaborating this. Okay, so this is about today's session. Yes.